How you doing?
Doing pretty good. Sorry I'm a little late. I was sending you the new homework
Oh,
problems.
okay. Let's see. So do I need to open something new here?
Yeah.
Okay. All right. Which page?
So it goes in order, starting with the one with the 7 in the top left-hand corner. Um,
Okay.
it's just a review assignment for tomorrow's test.
Okay.
So, and we're starting with number 12 on that page.
All right. So let me make sure I don't have anything else open that I shouldn't. Okay. And I've got this recorded. So f of x is equal to minus 5 times 2 to the x power. Well, if we're going to graph this, what's the parent function?
F of x equals x squared.
No, the parent function would be, and let's not call it f of x, because it's not the same as this. So let's call it g of x. And that would be 2 to the x. Okay? And
Okay.
if I graph 2 to the x, it looks just like every other exponential function. It looks like that, and it goes through this point right here. Because 2 to the 0th power is 1. So is 17 to the 0th power. In other words, this graph could just as easily be 17 to the x.
Okay.
Okay, it's hard to tell from looking at the graph what its base is what I'm trying to say. But exponential functions, as long as the base is greater than 1, look like this. They rise as x increases. So how is this different, this particular function?
Let's see. There's a negative 5 in the front, so it's flipping on
Okay,
the x-axis.
let's do that first. So this would be y equals minus 2 to the x. And then what's the consequence of the 5?
Let's see. That's gonna scale it by 5.
The vertical stretch by 5.
Okay.
Okay? And if you think about it, what it means is that every point that's on the blue curve is going to be 5 times further away from the x-axis. Okay, so if I take a point right here, and 5 times further away would be there, if I take my central point, which is now at 0, minus 1, and scale it by a factor of 5, where does it go?
I'm assuming down 5 points.
Yeah, down by a factor of 5, which means 5 times minus 1.
Okay.
Okay? Now, it still is asymptotic with the x-axis, but now it's a little steeper. In other words, vertical stretch factors make an exponential function be steeper.
Okay.
Primarily because every single point that's on the blue function is now 5 times further away from the x-axis because it's being multiplied by 5. Okay, so the red is the final function. Now, what's the domain of that function?
All real numbers?
Correct. Usually, in fact, I'm not sure I've ever seen an exponential function whose domain was not all real numbers. That's just the domain when you have exponential functions. What's its range?
Y is less than or equal to -1?
0. In other words, the horizontal asymptote didn't change. The horizontal asymptote continued to be the x-axis, which is y equals 0.
Okay.
Notice that as x goes to negative infinity, in other words, here's my function, y equals minus 5 times 2 to the x. Well, as x goes to negative infinity, this number becomes infinitely small. And even if I'm multiplying it by minus 5, it's still very, very close to the x-axis. In other words, it still never touches the x-axis, but it's asymptotic with the x-axis. And so the range is indeed y is less than 0, but it's not less than or equal to. There's no way to make y 0. No matter what you make x, y never touches the x-axis. What next?
Next one is 15.
Okay, this one has a lot going for it. In other words, there's a lot of adjustments to the parent function. First of all, tell me what the parent function is.
1/4 to the power of x plus 3?
Just 1/4 to the power of x.
Okay.
Okay. Now, because the base is less than 1, this one does not have the traditional shape. It has this shape here. Still going through that point 0, 1. In other words, any number to the 0th power is equal to 1. So the only difference between this and the last parent function, which was 2 to the x, is that it starts big and gets little, whereas the last one started little and got big. That's because when you take numbers less than 1 and you increase their exponent, they get smaller. Notice that 1/4 squared is 1/16. 1/4 cubed is 1/64. So if this base is less than 1, then this shape is going to go from big to little. If it's greater than 1, it's going to go from little to big. Okay. Now, we got 3 things going on. We got this, we got this, and we got this. Let's take them one at a time. Let's start with, well, and it's important to remember that whenever you're dealing with transformations, you always do reflections first. And it matters. You will get a different looking graph sometimes if you don't do your reflections first.
Okay.
Now, there are no reflections in this, so we don't have to worry about it. If there are no reflections, you can do them in whatever order you want. So let's do the 3 first. What's that do?
So that's a vertical stretch by a factor of 3.
Okay. What's it do to our primary point?
It's going to move it down 3.
Multiply both of these terms by 3.
Okay. So then you'll get the coordinates 0, 3.
Uh-huh. And it still has the same shape as our black curve. It just is vertically stretched. In other words, any point that's on the black curve is going to be now 3 times further away from the x-axis.
Got it.
Still would be asymptotic to the x-axis. In other words, if the only thing I was graphing was 3 times, in other words, what the red curve is, and I like to do these one at a time just so you can see, this is 3 times 1/4 to the x.
Got it.
Now, in green, let's figure out what the x plus 3 does. What's that?
Well,
what's that plus 3 going to do?
is it going to...
Remember this, Connor.
Mhm.
All translations that are inside the function are horizontal. All translations that are outside the function are vertical.
Okay.
This is inside the function. The 3, this 3 that's circled in red here, that was outside the function, right? Outside the parent function.
Right.
And the -1 is outside the parent function. So this 3 in red is a vertical stretch. This -1 circled in red is going to be a vertical shift. But the green is going to be horizontal in nature. And it's going to be a horizontal shift because it's added or subtracted to the x. Okay? Which way is it being shifted? To the left or the right?
To the left.
Correct.
Because it's in the parentheses.
Again, I'm going to take the only point that I know, that one right there, and I'm going to shift it 3 units to the left. So what are its coordinates now?
That's going to be -3, 3.
And in terms of the y-axis, I won't worry about that for the moment. Still going to be asymptotic with the x-axis. In other words, horizontal shifts do not affect horizontal asymptotes. They would affect vertical asymptotes, just like vertical shifts will affect horizontal asymptotes. But the green function is now y equals 3 times the parent function to the x plus 3. Okay? So we have one more only to do. We'll do it in blue. And that's the easiest one, really, the -1. What does that do?
Move it down 1.
Okay, so what happens to that point?
It goes down 1. So it becomes -3, 2.
Yeah, and now I can just draw my exponential curve, and that actually does change the horizontal asymptote. In other words, for my red, my green, and my black functions, I had a horizontal asymptote at y equals 0. Okay? Make sure you understand that the x-axis is defined by y equals 0.
Okay.
Y equal numbers are horizontal lines, x equal numbers are vertical lines.
Got it.
Well, I just did a vertical shift down 1. That means my horizontal asymptote got shifted down 1 also. So instead of now being on the x-axis, it's down there. So the blue line, as x goes to infinity, will approach my horizontal asymptote defined by y equal minus 1.
Got it.
So this curve here is what we were given, the entire thing, x plus 3 minus 1 outside the function. Now, what's the domain of this?
All real numbers.
What's the range?
Range is y is greater than -1.
Good. Good. Notice that log functions are really inverses of exponential functions. So when you look at log functions, the domain and ranges are going to be opposite, switched. In other words, just so that I make sure I cover it, here's a log function. Well, a log function's domain is what?
Domain?
Yeah. What's the domain?
Will it also be all real numbers?
No, this is a log function. In other words, this would be y equal log of x.
So would that be x is greater than 0?
Yeah. In other words, the same thing that the range was on exponential functions.
Got it.
And the range is what on a log function?
All real numbers?
Same thing as the domain was on exponential functions.
So it just switches.
It switches. And in fact, if I hesitate to tell you this because it can be quite confusing to realize that these are inverses of one another. This is y equal e to the x, and this is y equal natural log of x. Those are inverses of one another, and whenever you take the inverse of a function, you switch the domain and range. Also, they are reflections about the line y equal x. Notice the bottom black curve is a perfect reflection of the top black curve. Okay? So, even though log functions are inverses of exponential functions, do not get that confused with this. If I want to express this logarithmically, I have the log base e, which is natural log, of y equals x. That is not the same as that. Those are different. These two here are identical.
Okay.
One is not the inverse of the other. In other words, natural log of y equals x means exactly the same as y equals e to the x. And in fact, both of these are that curve. It just happens, notice the difference, this is y equal natural log of x, this is natural log of y equal x. So they're not the same. However, it is true that natural log is an inverse of exponential.
Got it.
But still, you can write exponential functions as log functions always, and where they're the same exact thing. Okay, I know that I had trouble with this when I first studied math, is that I got confused as, well, they first teach you that exponentials have a logarithmic expression, and they do, that is identical. These two are the same over here on the left circle. But they also have an inverse, which is a log function. But that is not the same as that. In fact, it's the inverse.
That's the, okay.
Okay? So just because you see log doesn't mean that it's necessarily the inverse of the exponential.
Okay.
It just depends on various things. So that was 15. What next?
Next one is 21.
Okay. Hold on a minute. Let me figure out how to move this. I guess I don't have to. Woo. So 21 says 8 to the third minus 3y equals 256 to the 4y. All right. Usually when you have equations where your variable is in the exponent, you have to use logarithms to solve them. That's almost the #1 rule. If your variable is in the exponent, you've got to use logarithms. There is one exception, and that is if I can make both bases have a common base. Well, 8 squared is 64, and 8 cubed is 256, is it not?
It's actually 512.
8 times 8 times 8 is 512. Okay. So what we have to do to solve this in a non-logarithmic manner, which is the way they want you to solve it, they don't want you to use logs, is we have to find a common exponential base where we can represent 8 as that base to some power, and we can represent 256 as that base to some power. Well, we just showed that 4, or 8 rather, is not that base. Nor is 4. I cannot represent 8 as 4 to any power. What I can represent is if the exponential base is 2. In other words, I can write 8 as 2 cubed. Same thing on the left, I haven't changed it. Now the key is, can I write 256 as 2 to some power? And yes, I can. 2 to the 5th power is 32. 2 to the 6th power is 64. 2 to the 7th power is 128. 2 to the 8th power is 256. Now I can apply my rules of exponents. What's this equal to? I got double exponentiation going on. What do I do with to the exponents?
Can you add them?
Multiply them.
Okay.
You add them when multiplication is going on. Over here on the right, if I have 3 to the 4th times 3 to the 5th, I add the exponents.
Got it.
Which is one level less than multiplication, notice. If I have division going on, 3 to the 6th divided by 3 to the 4th, I subtract the exponents. Subtraction is one level less than division. And if I have what I commonly refer to as double exponentiation, which is what that is, well, one level less is multiplication, so that becomes 3 to the 20th. This is probably the most important one to know. That's the one you have to use more frequently than any of them.
Got it.
So, what does the left side of this equation become?
9 minus 9y?
2 to the 9 minus 9y.
Oh, okay, sorry.
Equals what?
2 to the 32nd y?
Uh-huh. Now, another big principle is that if I have a base to one exponent equals the same base to a different exponent, then I can equate the exponents. I can say that 9 minus 9y has to be equal to 32y.
Got it.
Now you can solve for y. In other words, move the y's to one side of the equation, so you have 41y equals 9, which makes y equal 9 divided by 41. And there's your solution. Okay? Now,
Got it.
math is kind of famous for giving you these problems. I'm not quite sure why, because first of all, they give you these problems in the chapter on logarithms, and I could just almost as easily solve this using logs.
Mm-hmm.
Okay? In other words, it's only in these very, very special interests where I happen to be able to represent 8 as a power of 2, and I happen to be able to represent 256 as a power of 2. Well, if I can do that, then I can solve it in the way we just did. But turn that into that, and I can't do it anymore, right? In other words, I no longer have a way of representing 255 as a power of 2.
Got it.
So now what I would do is take the natural log of both sides. And now I would say 3 minus 3y times natural log of 8 equals 4y times natural log of 255. Well, these are just numbers. So I only have one variable, y. I would have to distribute the natural log of 8 to both terms, and I would have to distribute the 4y to this, and then I would gather all my y's together, factor out a y, and solve for y. So I can do these problems 100% of the time using logs. I can only do them maybe 5% of the time using common exponential bases, which is the way we did it the first time. In other words, when that was a 6, I can now represent 256 as a power of 2, and since I can represent 8 as a power of 2, then I can solve it without using logs.
Got it.
As an example, let me give you another quick example. 9 to the x equals 27 to the 2x. Solve that.
Using logs or without logs?
Well, which way can you do it without logs? Always try to do it without logs.
Okay. Let's see. You can take the base of...
Just because if it can be done without logs, that's the way they want you to do it.
Okay.
Okay, so is there a common exponential base between the numbers 9 and 27?
Yes.
What is it?
3.
Okay, so how do I write the next line?
Okay, so let's see. 3 squared.
In parentheses, very important.
Okay, to the power of x is equal to, let's see, is that 3 cubed?
It is.
Okay, to the power of 2x.
Okay, now when I do powers of exponents, I get 3 to the 2x equals 3 to the 6x. Now I can equate 2x has to be equal to 6x, and that is only true if x equals 0. So x equals 0 is our solution. And I did not have to use logs. Now, just something very interesting about using parentheses. What's this number equal to?
16?
Correct?
Okay.
What's this number equal to?
Let's see. 3 times 3, that's 27 to the power. A big number.
Huge number.
Okay.
And in fact, if you ever get into math at a level where there's a certain math topic that is the big numbers, you would think that big numbers would all be 10 to some power. Well, that's not the way they talk about big numbers. They talk about big numbers using that. The first time I saw it, I said to myself, well, why are they using 3? Why aren't they using 2? And it's because 2 to the 2 to the 2 doesn't get very big. It's 16. But 3 to the 3 to the 3, and the reason I bring this up is because if I don't use parentheses, you go from the top down. So this is the equivalent of 3 to the 27th power. As opposed to if I put parentheses around there, now it's 3 to the 9th power. Still a big number, but nowhere near 20 or nowhere near 7 trillion.
Right.
Okay. So, you know, if you really want to talk big numbers, you use this kind of notation. Imagine how big that number is.
Yeah.
Because I go from the top down, so that becomes 3 to the 7 trillionth power. One can only imagine how big that is. I mean, there's only...
I think they overflow on my calculator.
Well, yeah, really, exactly. There's this many molecules in the universe. 10 to the 50th. So there's all kinds of huge numbers greater than the number of molecules in the universe. In fact, math organizations had a contest once as to who could name the largest number. And the rules were you couldn't use infinity, you couldn't use somebody else's answer and add 1 to it. And the third rule was that it has to have some useful meaning. In other words, it has to either be the number of molecules in the universe or the number of atoms in the universe or some other exotic way of talking about gigantic numbers. But the way they refer to gigantic numbers is not so much using scientific notation, which is what we're taught. And this applies to most any number in our universe. But by using this kind of notation, they can get into truly big numbers. And they always use 3. They don't use 2.
Got it.
Just an aside that's kind of interesting. Most people would be shocked by the fact that 3 to the 3 to the 3 is 7 trillion times bigger than 2 to the 2 to the 2.
Okay.
Let's see, where are we at here? Which one next?
44.
Must be on the next page, maybe?
Yes.
44?
Yep.
That's upper right or lower left?
Upper right.
Okay. This only goes up to 29. You said 44?
44. Yep.
Or 24? 44?
44.
44. Well, let's check the next row, lower left. It still doesn't go up to 44. Let's check this one here. Bet this has it. There we go. Hold on. Don't get this program. Hold on. All right. God, I cannot move that over. How do I move that over? Now I get it. Okay. Let me write it. So we got the log base 5 of x minus the log base 5 of 2 equals the log base 5 of 15. All right. The way to solve log equations is to try to condense one side to a single log expression. In other words, if I can get the left side to be the log base 5 of some argument, then I can equate that argument to 15. Well, how do I use the rules of logs to turn that into a single log expression?
Can we use like the second principle? Say log base 5 to x over 2?
Uh-huh.
Okay.
Now, what can I say?
You can cancel out the logs.
Yeah, you're not really dividing by log base 5, but you can think of it that way. In other words, what's really going on here is if I have the log base 5 of A and it's equal to the log base 5 of B, well then A is equal to B. Okay, so I can say x over 2 equals 15, which is the same as dividing both sides by log base 5, even though that really is not what you're doing. This is not log base 5 times x over 2. It's more like f of x. That is not f times x, it's f of x. So take the log of an argument, it's not multiplication. It just so happens that the log of A equals the log of B, then A equals B as long as their base is the same. So x equals 30 is your solution. Now, the one thing about log equations you got to be very careful with is when you come up with a solution, you got to go back to your original function and make sure you don't violate any domains. In other words, remember that the domain is fairly restrictive on logs. This has to be a positive number. Can't even be 0.
Okay.
So x equal 30 is fine. But if I came up with a solution that said x equals 0 or x equal minus 1, then that means there is no solution, because you can never take the log of 0 and you can never take the log of a negative number.
Got it.
I'm sure they're going to give us one. What's the next one?
The next one is 47.
And you use your rules of logs on all of these. In other words, they all pretty much have the same common theme, is we're trying to make the left side into a single log expression.
Got it.
So what's the left side become?
My screen froze. Give me a second.
Okay. If you can even read it, do you have this document in front of you other than from my screen?
I do.
Why don't you look at it, and it doesn't matter if your screen is frozen or not. Tell me what the left side becomes.
Okay. Give me just one second.
Sometimes we can get beyond these technical glitches, sometimes we can't. But in this case, we probably can.
Okay.
So how do you combine those two log expressions on the left? Last time you did division of the arguments. What are you going to do this time?
Oh, now I multiply.
Okay.
So we distribute that down to...
n minus 4 is what the new argument is.
Okay.
Now we multiply that out.
Log base 4, n squared minus 4n is equal to log base 4 of 5.
Okay. Now what can you say?
Let's see. I thought is that n squared. Oh, now we can cancel out the logs.
Well, what you're really doing is equating the arguments.
Okay.
I hate to hear anybody even say you can cancel out the logs, because that's not really what you're doing. What you're doing is equating the arguments. If I have the log of some number equals the log of another number, well, then those two numbers have to be equal. So I can say n squared minus 4n equals 5. That's a quadratic. Let's solve for it.
What is it? N squared?
N squared minus 4n equals 5.
Oh, let's see, that's negative, x equals negative,
Well, first of all, let's put it in the form of a
positive
quadratic.
1?
N squared minus 4n minus 5 equals 0. And then let's factor it. So you get n and n plus minus.
It's going to be plus 1 minus 4, I think.
Minus 5. Remember, the two numbers have to multiply to
Right.
the constant.
Minus 5.
Okay? So that appears to give us a solution of n equals minus 1 and n equals 5, correct?
Correct.
However, if we go back to the original function, can n be minus 1?
No, it cannot.
That gets crossed out. That's no longer one of the solutions. The only solution we have is n equal 5. And
Now,
n equal 5 does not violate the domain.
if there are two positive answers, what do we do there?
Depends. In other words, if my positive answer was n equal 3, then it would violate that domain. In other words, the key is you cannot violate the domain, ever.
Okay.
If either answer, and almost always when, this is a very common problem. You're going to get this on any test, okay? And it involves turning it into a quadratic, factoring it, solving it, and usually when you solve a quadratic, you do get a negative answer and a positive answer. And almost always, one of those answers violates the domain. So you have to figure out which one. It isn't always the obvious one. It isn't always the negative number that violates the domain. In other words, my domain might be 3 minus x. So a negative x would not violate that domain. So you have to just test it.
Okay.
Now, notice one very odd thing. If, you still there, Connor?
Enjoy this Verizon ringback tone while your party is reached.
Connor, are you back?
Yeah, sorry, I got disconnected.
That's okay. I was going to call you and finish the audio by phone, but boy, you got back on very quickly. So can you now see my screen?
Yeah, I can see it now.
Okay, cool. Now, notice these two answers down here.
Uh-huh.
If I plug it into the second row, they don't violate the domain, not even the -1, because -1 times -5 is positive.
Right.
And that's almost always the case also. In other words, you will only see whether you are violating the domain by going back to the original function, which can be pretty confusing because we're kind of taught that those two are the same things. But clearly they're not exactly the same things. In other words, in the first row, I cannot have an n of -1. In the second row, I can.
Got it.
So if you don't go back to the original equation, you don't really see whether you're violating the domain or not.
Got it.
So you always have to go back to the original. Furthermore, these two are not identical. They're close. In other words, you can always take this log expression and turn it into this log expression. But no, for purposes of determining whether you violate domains or not, they're not the same.
Got it.
Okay. What's next on our list?
Okay. Next one is 53.
Which must be the next page. Three to the 5n is greater than 24. Round to the nearest 10,000th.
Would we take 3 and put it into as a factor for both?
No, factors, when you're dealing, this is an exponential inequality.
Okay.
Meaning the variable's in the exponent. Okay? When your variable's in the exponent, then you're not looking for factors of the base. You might be looking for common exponential factors, but you're not looking for factors. Well, there doesn't happen to be any common exponential factors between the numbers 3 and 24.
Got it.
However, I don't see anything that prevents me from taking the natural log of both sides. Now, you got to be a little careful when you're dealing with inequalities. You don't quite have the leeway that you have when you're dealing with equations. When I'm dealing with equations, I can do anything I want to the left side as long as I do it to the right side. Well, when you're dealing with inequalities, I can't quite do that.
Okay.
For example, I can't divide both sides by x in an inequality, because if x happens to be a positive number, I leave the inequality the same, but if it's a negative number, I got to turn it and switch it the opposite way. Therefore, you can't really divide by a variable. But
Got it.
I can take the natural log of both sides. Now, once I've done that, what can I do on the left? Remember, the whole reason for taking the natural log is...
Put 5n in the front.
Yeah, now we turn it into an algebraic inequality.
Got it.
Okay. Now I know that that is a positive number. So I'm able to divide both sides by 5 natural log of 3. So I end up getting n is greater than natural log of 24 divided by 5 natural log of 3. Now, let's talk about logs. How did I know that was a positive number?
Okay.
Logs of numbers greater than 1 are positive. Logs of numbers between 0 and 1 are negative.
Got it.
Remember what the log equation looks like. Looks like this. That number always being 1 comma 0. And I could say that that's y equal, I can use common log or any base log I want. They're all going to look like this. Well, notice that when my x is less than 1, all my y values are negative, all the way down to negative infinity. But when my x values are greater than 1, all my y values are positive.
Got it.
So that's key on this. Oh, now it's going to go the other way on me. Hold on. I guess this is what I want, yeah. Now, that's important on this problem, very important, because if I don't know whether one of these things, in other words, the way I'm going to solve for n is I've got to divide by 5 times natural log of 3. Well, so it's extremely important to know whether that's a positive or a negative number, because if that's a negative number, then I got to switch the direction of the inequality.
Okay.
In other words, if it was natural log of 1/2, now the next line, I'm still going to divide by the natural log of 1/2, but I'm going to turn the inequality sign around because I know that I'm dividing by a negative number.
Got it.
So I don't see very many of these problems. In fact, that's probably the first exponential inequality problem that I've seen in 5 years. Serious.
Wow.
Yeah, you don't get it much. Which school do you go to, Connor?
STEM Academy.
Ah, that's why. That's why. If you were going to just a regular high school, you would not see this problem. But when you go to one of those special schools, they go quite a bit above the Common Core. And this is an example of it. You would not see this problem in Common Core. but a lot of schools will go way beyond Common Core.
Right.
It's the next problem. We only have 3 or 4 minutes, but maybe we can cover one.
Okay. Give me a second here.
That was 53.
Oh, it says the next one is 60.
60?
Yep.
Let's see whether we can do 60 quickly. We got natural log of x plus 3 equals 5 less than 5. Now, when you have a log equation, in other words, what we just dealt with was an exponential equation. We solved it by taking the logs of both sides. Well, when you have a log equation, you usually solve it by converting it to exponential. In other words, you always solve it by doing the opposite.
Got it.
How, if this was an equation, instead of, in other words, let's start by pretending the problem says this. And then we'll figure out whether we can use the same logic on inequality. Well, what is the exponential expression of that?
Oh, let's see. It would be x plus 3.
Hold on. It's the number on the far left. In other words, it's the base.
Okay, so e?
E to the 5th, the number on the far right, equals everything in the middle. X plus
3 to the 5th.
To the 5th. Now I can solve that. That's an exponential equation. I can get that number out of my calculator. I can take the 5th root of it. I can subtract 3, and I come up with x.
Got it.
Okay? So solving a logarithmic equation is relatively straightforward. You just put it in exponential, and generally you can figure it out from there. In other words, I'd be able to solve that easy. That's algebra.
Got it.
Now, the question is if everything the same when it's that? In other words, can I continue to say that e to the 5th is less than x plus 3 to the 5th? And I believe I can.
Okay.
When I say I believe, it's because I'm not sure I've ever had to solve one of these.
Really?
Yeah, where you start with a logarithmic inequality and you solve it. But this got to be the only way to do it. E to the 5th will be a number, so it's a positive number. So I can take the 5th root of both sides. Okay, so I've got e to the 5th. That's taking the 5th root of the left side. Leaves me e. And leaves me that on the right side. So I get e is less than x plus 3, which means x is greater than e minus 3.
Got it.
That's assuming we can do that. If you can't do that, I have no idea what they expect you to do. Although it is interesting that we got x being possibly negative. In other words, x could be negative 0.1. Still satisfies our answer. But notice that even if x is negative 0.1, or for that matter, it can be, up to negative 0.7, it still makes the argument positive because the argument was x plus 3. So we don't violate any domains. I don't honestly know the rule between converting natural log to exponential as to what governs whether you can do it or not. In other words, if it's an equation, we can definitely do it. If it's an inequality, well, not all rules that apply to equations apply to inequalities, but probably in their example, they give you, no, they just do an equation. They don't do an inequality in their example. They do an inequality up here. And they appear to treat it exactly like an equation. So I guess for purposes of your test, treat inequalities just like equations.
Okay.
Okay. All right, Connor, I will let you go.
Awesome.
Have a good week, and I'll talk to you next time.
Awesome. Sounds good. Thank you very much.
Bye-bye.